Welcome to the Introduction to Battery Technology course. This lecture focuses on Chapter 6, which discusses lithium batteries. Chapter 6, Lithium Batteries, is divided into 3 lectures, and this is the first lecture in the series. Learning objectives. In this session, we'll explore the fundamentals of lithium battery technology, with a special focus on the lithium-ion batteries that power modern electric vehicles. Our goal is to help you understand how these batteries work and how this knowledge connects directly to manufacturing, assembly, and maintenance on the production floor. Lithium is the lightest metal on the periodic table. It's so light it can float on water, and that's part of what makes it ideal for high-energy batteries. It has strong electrochemical potential, which allows lithium-ion batteries to deliver high power while staying compact and efficient. By the end of this chapter, you should have a solid foundation for understanding the processes, materials, and challenges involved in making lithium-ion cells. In this slide, we're introducing some of the terms you'll often hear in lithium battery manufacturing. These include lithium, coulombic efficiency, dendrite, shuttle effect, ionic conductivity, and polysulfide dissolution. Let's focus on 2 of the most important ones here. First, dendrites. These are tiny, needle-like lithium structures that can grow from the anode during charging. If they get long enough to pierce the separator, they can cause short circuits and even fires. The picture on this slide shows how dendrites can grow and create a short circuit path. Second, ionic conductivity. This describes how easily lithium ions move through the electrolyte. High ionic conductivity means smoother current flow and better battery performance. You don't need to memorize every term right now. Throughout your training and work on the factory floor, you'll keep encountering these and many more. The goal is to start recognizing them and understanding why they matter for safe, high-quality battery production. Lithium battery. Advantages and disadvantages. Here we have a quick comparison of lithium batteries, their strengths and their challenges. On the advantage side, the key takeaway is their high specific energy. They pack a lot of power into a small, lightweight design, which makes them ideal for electric vehicles. They also have very low self-discharge, meaning they hold their charge for a long time when not in use. But there are disadvantages we must always manage in production and operation. The biggest concerns are safety risks, such as fire or explosion if the cell is damaged or overcharged, and the formation of dendrites, which can lead to short circuits. Take a moment to look through the rest of the table on your own. You'll see how these advantages and limitations balance each other, and how careful design and control in manufacturing help us keep the benefits while minimizing the risks. Lithium battery types. Now that we've covered the basics, let's look at the different types of lithium batteries. First, they can be categorized by several factors: by electrolyte type, liquid, gel polymer, or solid; by anode material, lithium metal or lithium ion using graphite or silicon; and by application, such as consumer electronics, electric vehicles, aerospace, or energy storage systems. The table shows some key examples. Lithium metal batteries are primary, meaning they're not rechargeable. You'll see them in coin cells or military devices. Lithium-ion batteries are secondary or rechargeable, and these are what we use in EVs. Lithium polymer batteries are similar to Li-ion, but use a gel polymer, making them lighter and more flexible, common in drones or portable devices. Solid-state batteries use solid electrolytes and are still being developed for next-generation EVs, offering higher safety and energy density. For your work in production and maintenance, the focus will mainly be on lithium-ion systems, but it's important to understand where they fit in the broader battery landscape. Solid-state lithium metal batteries. Now let's talk about solid-state lithium metal batteries, or SSBs, the next big step in battery technology. Unlike today's lithium-ion batteries that use liquid electrolytes, these use solid materials, ceramics, sulfides, or polymers, which means no leakage and far less fire risk. The lithium metal anode gives them extremely high capacity, about 30 to 50% more energy than standard Li-ion cells. That means longer range for EVs or smaller battery packs for the same power. But, as the image shows, they still face some challenges. Chemical reactions at the interfaces, cracking from volume changes, and thermal stability issues if the cell overheats. So while they promise safer, higher density batteries, there's still engineering work ahead before they're ready for mass EV production. Lithium polymer battery, LiPo batteries are a type of lithium-ion battery that uses a solid or gel polymer electrolyte instead of a liquid. This design makes them lightweight, thin, and flexible, as shown in the pouch structure here. They're safer because the polymer reduces leakage and prevents dendrite growth, and they perform well even at higher temperatures. You'll find them in drones, phones, and compact devices where space and weight matter. Lithium metal battery. LMB lithium metal batteries are primary, meaning they're non-rechargeable. They use pure lithium metal as the anode, giving them very high energy density, much higher than standard Li-ion cells. They're commonly used in coin cells, cameras, and military equipment because of their long shelf life and stable voltage output. However, once discharged, they can't be reused. That's the trade-off for their high performance. Lithium-ion battery, Li-ion/LIB. Now, we're looking at how a lithium-ion battery actually works. One of the most important systems in today's EVs and electronics. It's a rechargeable system that relies on the movement of lithium ions, Li, and electrons, E, between two electrodes, the anode and the cathode. Let's break down its four main components. The anode, usually made of graphite, stores lithium ions during charging. The cathode is typically a metal oxide, such as LiCoO2 or LiFePO4, which releases lithium ions during charge and receives them during discharge. The electrolyte, a liquid containing lithium salts, carries Li ions between the electrodes. The separator keeps the anode and cathode apart to prevent short circuits while allowing ions to flow freely. During charging, lithium ions move from the cathode to the anode through the electrolyte, while electrons travel through the external circuit to the anode, storing electrical energy. During discharge, the process reverses. Ions return to the cathode, and electrons flow through the external load, creating an electric current that powers devices. So, in essence, the flow of ions inside and electrons outside the cell works together to store and deliver power efficiently. Lithium-ion battery, performance characteristics. In this slide, we're looking at how we evaluate the performance of lithium-ion batteries. The chart here shows 6 key characteristics. Each axis represents one property, and the farther out the shape extends, the better the performance in that area. Let's quickly go through these 6 parameters. Specific energy. This shows how much energy the battery can store per unit of weight. Higher values mean longer range for EVs. Specific power measures how quickly the battery can deliver energy. This affects acceleration and response time. Safety refers to stability under stress or abuse conditions, like overheating or short circuits. Performance, how well the battery operates under various temperatures and demanding conditions. Lifespan, the number of charge-discharge cycles the battery can handle before its capacity drops significantly. Cost, the overall manufacturing and material expense remains a key challenge for large-scale applications. Each lithium-ion chemistry, NMC, LFP, LCO, etc., balances these 6 factors differently. For example, some chemistries trade off power for safety or energy for cost efficiency. This chart helps visualize those trade-offs before we explore specific types in the next slides. Types of lithium-ion batteries. Here, we're introducing the main types of lithium-ion batteries, both in terms of chemistry and cell format. All lithium-ion batteries share the same basic design: a graphite anode, a lithium-based cathode, and a liquid electrolyte that allows ions to move. What makes each type different is the cathode composition, for example, nickel, cobalt, manganese, or iron. These materials determine key properties such as energy capacity, safety, cost, and lifespan. There are 6 major lithium-ion chemistries: NMC, NCA, LFP, LCO, LMO, and LTO. Each has its own balance between power, energy density, and safety, which we'll compare in the next slides. Visually, you can also see the 3 main cell form factors: cylindrical cells, common in power tools and EVs like Tesla. Pouch cells, thin and flexible, are often used in consumer electronics. Prismatic cells, rectangular and durable, are suitable for automotive and energy storage systems. In addition, there are button-shaped cells. Understanding both chemistry and form factor is key to selecting the right battery for a specific application. Types of lithium-ion batteries, performance matrices. In this slide, we compare the 6 main lithium-ion chemistries based on their performance characteristics: energy, power, cost, safety, lifespan, and performance under temperature extremes. The shape diagrams show how each battery type balances these 6 traits. The farther the colored area extends along an axis, the better that performance. Let's focus on the key ones used in EVs: NMC, nickel manganese cobalt, and NCA, nickel cobalt aluminum. Both are nickel-rich and offer high specific energy, meaning longer driving range. However, they need careful management for safety and thermal stability. LFP, lithium iron phosphate, has lower energy density but provides excellent safety, long cycle life, and low cost, making it ideal for buses and entry-level EVs. The others, LCO, LMO, and LTO, are more commonly found in portable devices or specialty applications where compactness, safety, or long lifespan are prioritized. The main takeaway here is that no single chemistry is perfect. Engineers choose the right balance depending on whether energy, power, cost, or safety is the top priority. Influence of Ni/Co/Mn/Fe in cathode materials. By adjusting how much nickel, cobalt, manganese, or iron is used in the cathode, battery chemists balance energy versus stability. Increasing nickel content raises energy density and capacity, but makes the cell more fragile and less thermally stable. More manganese or iron improves safety, lifespan, and structural stability, but lowers energy density. Cobalt helps stabilize the crystal structure and enhance cycle life. But because it's expensive and limited, it's used sparingly to balance cost and performance. Be sure to review the table on this slide carefully. It summarizes each element's primary strengths and trade-offs, showing how they influence battery performance, safety, and cost. Nobel Prize and the birth of lithium-ion batteries. In this slide, we take a moment to appreciate how modern lithium-ion batteries began. The 2019 Nobel Prize in Chemistry recognized John B. Goodenough M., Stanley Whittingham, and Akira Yoshino for their pioneering work that made rechargeable lithium batteries possible, a technology that now powers nearly everything around us, from smartphones to electric vehicles. On the left, you can see why lithium is so special. It's the lightest metal, and its single outer electron can be easily released, forming a lithium ion that carries charge. On the right, Whittingham's early design showed how lithium ions could move between the anode and the cathode, generating electricity in a controlled way, a foundation for today's batteries. The Nobel recognition reminds us that fundamental chemistry research can lead to world-changing technologies, something every engineer and technician in this field continues to build upon. This concludes Lecture 1 of 3. Please proceed to Lecture 2 of 3 to continue.